Welcome to another session of Introduction to Photonics. So, we will start with a slightly different topic today. So, we have been discussing optical amplifiers till the last lecture, and even the last lecture promised that we will get on to looking at fundamental principles of lasers. We did not get an opportunity to do that in the last lecture, but let's get started with that. So, when we talk about a laser, what are the things that come to our mind? What do we associate a laser with? The properties of the laser, the coherence, right, both in terms of spatial as well as temporal coherence. So that actually leads to high directivity, very narrow spectral width emission, and so on. So, how do we go about building a laser, and then what are the characteristics of the laser is what we will look at now. This part we already discussed briefly previously, right. So, a laser is going to consist of a gain medium, right, which it provides gain as long as you can provide this external excitation, which we call as the pump, right. The pump is required to take this medium above thermal equilibrium conditions, and then we know that it is going to excite the atoms in the gain medium to a higher energy level from which you can achieve stimulated emission. And we said we will make a laser by providing feedback. So, we will put a mirror here and another mirror here, right. Let us call this mirror with reflectivity R1, let us call this mirror with reflectivity R2. So, that those provide the feedback. So, when you have these excited ions initially providing spontaneous emission, and then with feedback from either ends, you are actually able to provide able to get stimulated emission, and then we get laser output, right. The laser output could be from just one end, or it could be from this end also, right. It depends on what is the relative reflectivity of the two mirrors. Okay. Typically, what we do in a laser is we provide, we want to get directional radiation. So, we want everything to come out of one end. So, what we do is we try to make R1 close to 100%, as close to 100% as possible. So, there is very little light coming from that side, and R2, which is normally called as a output coupler, is something that is a partially reflecting mirror, which means that it will allow part of the light that is within the cavity to escape, and then you can get the laser output from this end, right. Now, the question is, what are the conditions that you need to satisfy so that you can get that laser output. Okay. So, one of the conditions that you need to satisfy is, if you are looking at the fields corresponding to the radiation inside the cavity, let us say we are starting with a field with amplitude E naught, right. E naught, that field is going to, as it propagates through the gain medium, it is going to obviously get certain gain, which we call as the gain coefficient is gamma. So, since we are dealing with the fields instead of power values, we say the gain coefficient, the actual gain that you get is actually gamma by 2. If I was tracking power, I would basically say P naught into e power gamma times the length, right. But since I am actually looking at tracking the field, I am actually writing it down as gamma by 2. Why am I tracking the field? Because I not only want to match the amplitudes, but also the phase. I want to also track the phase, right. To track the phase, you need to see what is happening to the fields. Okay. So, if we say that the length of the cavity is L, then within one round trip, right, it's traveling a distance of 2L. I made it look like the cavity length here is equal to the length of the gain medium, right. So, that is typically the case. Okay. So, although I have drawn it with a certain gap between the gain medium and the mirrors, typically you can consider that the length of the gain medium is actually the length of the cavity. Okay. So, it's going through a gain according to e power gamma times L, but it might also go through certain losses in the cavity. Okay. How do you represent the losses? Now, of course, it could actually, when light is propagating through this medium, there could be some scattering centers, there could be some spurious absorption centers. There are certain ways that you can lose photons within the cavity. So, that loss, I would call it as the loss coefficient is alpha int, and once again, since we are tracking fields, I would say alpha int divided by 2 multiplied by 2L corresponds to all these background losses, and then you also have losses at the mirrors, right. So, only root of R1, which corresponds to the reflection coefficient for mirror 1, and root of R2 corresponds to the reflection coefficient for mirror 2, only that is sustained in the cavity, right. And then of course, it accumulates phase as it is traveling within the cavity. So, that phase is accumulated as e power minus j k naught, where k naught is the wave number, multiplied by, once again if we say the refractive index of this medium, we call it as n. So, n times 2 times L is the phase that you accumulated within a round trip. Now, laser oscillation is possible. So, the condition for laser oscillation is that this equals to E naught. Essentially what we are saying in writing all of this down is you are able to sustain the fields upon round trips, upon consecutive round trips, right, such that the gain that you have is enough to offset all the losses within the cavity, right, and then you are able to sustain the fields within this structure. So the question is, we are tracking the initial field to the round trip field, whether R1 and R2 are accounting for the The losses, yeah. Basically what we are saying is only a certain fraction of that field is going through the round trip, right. So we are accounting in the round trip, we are accounting for the losses because of the finite reflectivity. The question is, how is this then equal to that? That is the condition we want to achieve. We want to say that is actually sustaining the fields. Okay. So that is you can call that as the threshold condition, where the loss is met by the gain. So the question is, why should it be E naught? Well, E naught is the original field without amplification, but after amplification, where the amplification is denoted by what's happening over here, right, that is the amplification term. After amplification, the fields are certainly increasing, right, it is a higher value, but it still has to overcome the losses within the cavity, right. So, we are basically saying this is the minimum condition to achieve laser oscillation, right. So, this actually gives rise to two conditions. One where you can say that the phase condition is going to be satisfied if k naught multiplied by n multiplied by 2l is integral multiples of 2 pi m, right. So, that is basically the constructive interference condition, right. So, the phase will be satisfied if k naught multiplied by n multiplied by 2l equal to 2 pi m, and then the remaining parts, the amplitudes, are going to be satisfied when this exponential term e power gamma l multiplied by e power minus alpha int l multiplied by root of r1 r2 equal to 1, right. So, that is the other condition that we get. So, we can rewrite that. So, basically we are saying that when you are looking at the amplitude, you are saying e power gamma l e power minus int l multiplied by root of r1 r2 should be equal to 1, right. So, those are the two conditions that we get as a result of making sure that the fields are consistent upon a round trip. Okay. So, I can take this expression on the left side and basically do a ln of that, and then I can get a slightly modified expression. So, let me call this as equation 1 and let us call this as equation 2, and equation 1 provides, if you just rearrange the terms, what you get is gamma is going to be equal to alpha int plus 1 over 2l ln of 1 over r1 r2. Okay. So, where do I get this factor 2l? Well, the L is straightforward, right. We had gamma L and alpha int L. So, we are just taking that and loading it on this reflectivity term. But where does the factor of 2 come into the picture? It's the square root, right. So, since you have a square root there, you have taken that half out, right. So, this is one important condition that needs to be satisfied. Essentially, we are saying that the gain in the cavity has to be sufficient to overcome the losses in the cavity, and that is when you get laser oscillation. Okay. So, that is one important result, and the other important result is what we are saying is 2 pi over lambda multiplied by n multiplied by 2L is equal to 2 pi multiplied by m, and lambda you can write it as c over nu, where nu is the frequency. So, you based on this you get the result that nu has to be equal to m into c over 2 times n L, right. So, there are only certain frequencies that can be sustained within that cavity. Okay. So, there are certain frequencies which are given by m into c over 2 n L, where m is an integer, right. So, only those frequencies survive within the cavity. So, if you put this all together, if you say for example, this entire loss you just load it on one term, we call it as resonator losses alpha r. Okay. So, we can visualize it like this, right. So, let us actually track the gain as a function of frequency. Okay. We have a certain for a given cavity we have a certain loss that is given by alpha r. So, that is the level that we have. So, both gamma and alpha r in terms of inverse centimeters, or you can think of it as inverse meters, right. When we look at the overall gain, what we will find is for a given gain medium, you may have at low powers, you may have something like this, and as you increase the power level, or maybe I can just put this in dotted lines over here. As you increase your pumping rate, okay, your gain is going to pick up, right, and beyond a certain point you are going to have sufficient gain to overcome the losses in the cavity, right. But that still does not mean that all these frequencies exist in the cavity. What the second condition is telling us is there are certain longitudinal modes of the cavity, only certain frequencies these frequencies are spaced by c over 2 times n L, okay. Only those frequencies survive inside the cavity. So, what this actually says is any of these lasers that you look at, okay, it is going to consist of multiple longitudinal modes. We are saying longitudinal modes because these is a mode that is consistent with the cavity along the axis. This is to be differentiated from the other type of modes that we have been looking at when we are looking at optical fibers and other waveguides, right. Those are called transverse modes. Those are transverse to the direction of propagation, right. The transverse distribution is what we call as transverse modes, but this distribution which is because of the mirrors at the ends, right, and in the longitudinal direction, these are giving rise to what is called longitudinal longitudinal modes. So, when somebody tells you we have several modes in the laser, you are given a laser with several modes, you first want to ask the question, is it longitudinal modes or transverse modes, right. So, the transverse modes obviously you can have as far as a fiber is concerned, you can have this LP01, LP11, LP02 modes and all that. And these longitudinal modes are essentially comb of frequencies that are supported by the laser. Okay. So, this is not something that is very obvious. When people say laser, they say okay, it is occupying this much of the spectrum, and they look at it as a continuum, the spectrum as a continuum. But if you look at the output of the laser with enough resolution, enough spectral resolution, you will actually be able to make out that there are multiple longitudinal modes with equal spacing in the laser spectrum, right. So, is that clear? Yes, it's a question. Yes. Yes. So, the overall spectrum will be determined by those modes that are meeting the threshold condition. So, the envelope of that, you look at the envelope of that and you look at the full width half maximum of that. That is what people look at it as a spectral width. That is the total width that is occupied by all the longitudinal modes, right. So, you have what is called full width half maximum. So, half from the maximum, but the complete width, that is called the full width half maximum. So, when people refer to the line width of a laser, they talk about the full width half maximum of this, and within the line width there could be multiple modes. Now, of course, under some very special conditions, you can have only one mode oscillating within the cavity as well. Okay. We will come back and look at that special case later on, but if there is only one longitudinal mode operating the laser, that will correspond to a very narrow line width, okay, and those would be called a single longitudinal mode laser. Okay. But how we get that and all are details that we can come back to later on. Okay. So, what we are saying, in other words, is for laser oscillation, we need to have the gain coefficient greater than alpha r. Okay. We need to have the gain coefficient greater than the resonator losses. Okay. Now, if we try to simplify the picture, let us assume that alpha E equal to alpha A sigma E equal to sigma A equal to sigma, which is the emission cross section. If it is equal to the absorption cross section, we know that is a very special condition, but if we assume that, then we can just say that sigma multiplied by n, where n is what? N is the inversion, right. So, sigma multiplied by n has got to be greater than alpha r, or n, okay, there is a threshold n, right. There is a minimum inversion that you need to have, which we can call as the threshold inversion. There is a threshold population inversion which is given by alpha r over sigma. Sigma is the transition cross section. Okay, just looking at a very simplistic picture. So, your inversion has to be greater than that, so that you can achieve laser oscillation, and what we also are saying is that as you this is actually as a function of pumping rate, right. So, what we are looking at is increasing pumping rate. As we have increasing pumping rate, you get over this condition where you get over the loss inside the cavity. And now let us see if we can express this in terms of a slightly different quantity rather than looking at alpha r, which is the resonator losses. Let us look at it from a perspective of the average lifetime of a photon. Okay. So, what do I mean by the average lifetime of the photon? It basically, the photon bounces around for a certain time before it escapes the cavity. Okay. So, let's look at, for example, the equation number 1 a little more detail. What does R1? So, to get the to get a very low threshold, or to get to the threshold condition with very low pumping rate, what do you want to have in your cavity? Certainly, you want to have very low losses, background losses. So, you start with a material, gain material, which does not have very many scattering centers, which does not have very many background absorption and all of that. So, you start with a very pure gain medium. But what can you say about the reflectivity of the mirrors? Where will you get very low threshold? Under what condition, what reflectivities do you get very low threshold? Reflectivity closer to 1, right. So, that's 100% reflectivity. So, if you have 100% reflectivity theoretically, right, then you get the the lowest losses, right, and then it's easier to achieve that inversion. Okay. So, if you have very high reflectivities, what can you say about the lifetime of a photon? Assume that you have 0 losses, the alpha int is 0. So, the photon is going to keep bouncing around for a very long time. So, higher the reflectivity, when we are talking about Fabry-Perot interferometers, we were talking about finesse of the Fabry-Perot cavity. So, this is actually a Fabry-Perot cavity, right. So, if you have very high finesse, that means the photon spends a large amount of time, a relatively long time bouncing around. So, the lifetime is larger. So, I can say that if I am expressing in terms of the photon lifetime, and I would say that this is the average photon lifetime, because this could be statistical, just like anything that we have discussed so far as photons concerned. You can only talk in terms of an average value. That average photon lifetime, if I calling that tau photon, tau photon is going to be inversely proportional to alpha r. If the resonator losses are very low, then I am going to have a long photon lifetime. On the contrary, if the resonator losses are very high, the photon is going to either escape the cavity very quickly, or the resonator losses could be high because of lot of background absorption, in which case the photon vanishes because of the background absorption, right. So, the average lifetime, photon lifetime is going to be inversely proportional to alpha r. And if we were to get to since we are talking about photon, that proportionality constant has to be equal to the velocity, right. So, you can just write it as c multiplied by alpha r, where c is the velocity of light, right, the velocity of which the photon is traveling. Okay. Now, of course, we say c in general as if it is a free space cavity, but if you were to be technical about it, if it is actually a cavity with refractive index n, then c over n would correspond to the actual velocity of the photon. Okay. So tau photon is given by this, which obviously you can write it alpha r is equal to 1 over c into tau photon, and this we can now substitute in this expression nth equal to alpha r over sigma. So, this implies that the threshold inversion is going to be given by 1 over c times tau photon multiplied by sigma. It's just a different way of writing it, but nevertheless, this is the inversion with respect to the average lifetime of the photon inside the cavity. So, now I think we have enough material to see what happens when you turn on a laser. Okay. So, can we just try to visualize it, and to visualize it, what we actually need to look at is the saturation of the gain. So, the gain as a function of the signal photon flux, right, which we know is going to be like this, right. And in this, I would say that, let us say this corresponds to the level of losses in the cavity. Okay. So, I turn on the laser, right. When I turn on the laser, I am pumping some photons which are getting absorbed in the gain medium, and that absorption results in the emission of certain photons spontaneously. Okay. And those photons upon feedback are going to start stimulating certain transitions, okay, and you start building up the stimulated emitted photons. Okay. So, what we are doing in that case is you may start here. So, this is your starting point, but as you build up the photons inside the cavity, you are going to saturate the gain medium, right. So, the gain is actually going to decrease as you build up the photons inside the cavity, and it may decrease to a point even below alpha r, right, at which point your stimulated emission, is not as much. So, you are basically having spontaneously emitted photons, and those photons are going to be very few, right, because of which you go back to the small signal regime, right. So, you start going past here and then you realize, oh no, we have very few photons coming around. So, the gain actually corresponds to the small signal gain. So, then you go up, right, and you may go past this point also, but then as you build up photons, you are coming back to this point. Okay. So, from the point you start the laser, when you turn on the laser, this is what happens. You are immediately getting some the moment you start pumping it, you start getting some spontaneously emitted photons. Those photons are going to bounce around, right, and they are going to stimulate certain, they are going to create stimulated emission. So, the stimulated emitted photons are going to build up, but even as they are building up, they are starting to saturate this the gain medium, and you may saturate to a fairly high level, in which case you have very few photons in the cavity, and so you are picking up on the gain, right. So, you are going towards the small signal gain, and then finally. So, finally, after all that, you started there and you would end up over here. Okay. You would end up at the point where the gain equals the loss in the cavity. So, you can understand this a little more easier if we look at it as a function of time, and we are looking at let us say the output of the laser, the output power of the laser. So, this is the time at which I decided to flip the switch, turn on the pump, right. Then I am going to have a high output, and then as you have the high output, you starting to saturate the gain medium. So, you are going to come down, and then when you come down, you have fewer photons. So, you can actually pick up on the gain. So, you are going to go up, you are going to do this and finally reach a steady state value. Okay. So, these sort of oscillations are what you call as relaxation oscillations, right. So, you have relaxation oscillations corresponding to this gain saturation that you are having, and gain saturation and then gain recovery, saturation recovery. That is what is happening, and that is what causing those oscillations. So, the question is, can we plot against output as a function of pump power? So, output as a function of pump power is what we are looking at over here. As you increase the pump power, okay, or maybe I can based on this, I can draw one more picture. So, let us just say output as a function of pump power, right. So, what we are saying is that output is going to be fairly low. Beyond a certain threshold, it is going to pick up in terms of the output power. And so, what exactly is happening over here? So, this region, you are essentially it is dominated by what process? By spontaneous emission. and as you build towards the threshold, right, you are actually building up the stimulated emission, and what you can say is this region is dominated by stimulated emission. So, the relaxation oscillations that we are showing is, suppose I am turning on with this much pump power, right, I am turning on at this much pump power, and this is actually showing that it is above the threshold, right. So, it is above the threshold condition as far as your gain is concerned, but still from a perspective of photons, the photons have to build up. So, there is a finite time over which the photons build up, and as they build up to a high enough value, they start saturating the gain, right, and because of that the photon, the number of photons are decreasing, and then you say, okay, because the number of photons are decreased, it is not as much saturated, the gain medium is not as saturated, so the gain recovers. Okay. So, if you look at the microscopic picture, the what is happening from the photon perspective, you can actually track all these processes really well. Okay. So that is what we have as far as the laser emission is concerned. Okay. So now what we actually need to do is we need to consider this gain saturation. So we are basically saying the gain saturation is a very integral part of this laser emission. So we need to when we were talking about gain has to be greater than alpha r, that gain has to now account for the saturation as well. Okay. So now I need to modify this expression a little bit. So how do I modify that? Basically I would say that the actual gain would correspond to the small signal gain divided by 1 plus the signal flux divided by the saturation flux, right, and the signal right. So the signal flux is actually as a function of frequency as well, right. So this has got to be equal to alpha r at threshold. Okay. And I say it has to be equal to alpha r at threshold, but in the picture that we showed, even though you are pumping at a higher rate, even though you actually have your small signal gain greater than alpha r, right, through the process of saturation, you are going to get eventually clamped at a point where your gain, your saturated gain is equal to alpha r. You are just meeting that condition. So any more pump photons beyond that condition is actually converted to signal photons. You see what is happening? So I am actually having lot of pump photons go into the medium, right, and it is creating some signal photons. There are certain signal photons that are required to meet the losses in the cavity, right. Any more pump photons that I put beyond that, that is actually going to get leaked out as your laser emission. As far as the medium is concerned, the gain medium is concerned, the gain is actually clamped at that alpha R value, the resonator loss value. So, in this picture over here, what are we saying? As we increase the pump power, we are getting to the point where we have a threshold, right? We have a threshold pump power. Beyond that, you are essentially whatever pump photons that you put is actually getting converted to signal photons. So, the output of the laser, any increase in the pump photon in the pump power corresponds to an increase in the signal power, right. But in that process, what we are saying is beyond this, it does not mean that the gain is increasing, the small signal gain is increasing as a function of pump power, but the saturated gain gets clamped at this alpha R value, right. So, you are just meeting that condition, and whatever other pump photons you have is actually escaping the cavity as signal photons. You understand that? Okay. So, if you have this condition, then you can rewrite this, you can rewrite this expression in terms of phi s. Okay. So, let me just grab this. The question is what happens to the signal photons that we are giving into the system. For an amplifier, you have some weak signal photons coming in, you are getting amplification, right. Laser, you are not giving any signal photons to start with, it is actually self-seeding through the spontaneous emission of the system. Now, the spontaneous emission, as it goes through these reflections, it has to get in tune with the cavity, right. Only certain frequencies are allowed. So, the spontaneous emission may be broad, but only certain frequencies are allowed by the cavity, and the photons at those frequencies will actually go through stimulated emission, and that is what is giving you the comb structure as far as the spectrum is concerned. Okay. So, there are no external signal photons that you are giving, you are just providing pump photons to the system. I should just say pump energy to the system, because we are talking about a case where we are using light energy to get this laser going. We were going to go into semiconductor lasers where we are giving electrical energy to the system, and through that we are getting light emission. Okay. We will look at that later. But yeah, in general, through that external energy, we are initially getting spontaneous emission, and from that you are building up, you are refining and you are building up stimulated emission at specific frequencies that corresponds to the longitudinal modes of the laser. Okay. An interesting thought here. Okay, let's see how well you know about your mathematical signals. Now, if I have a comb of frequencies, right, if I have a comb of frequencies like this, if I take a inverse Fourier transform and look in the time domain, what should I see? If I have a comb of frequencies, if I do an inverse Fourier transform, what should I see in time? Pulses. You should see pulses, right. So, if the laser was working perfectly, if you have this comb of frequencies, right, corresponding to that, if you look in the time domain, you should actually have a train of pulses. You do not see that when you take a laser, and normally when you operate the laser, you look at the output, it looks like it's continuous output. Why? You will get pulses if all of these longitudinal modes are locked in phase. If they are all oscillating synchronously, you will get pulses. But when you think about practical lasers, they are operating at some ambient conditions. You have basically the medium is subjected to certain temperature, certain perturbations, that you do not have a good phase relationship between the longitudinal modes. Okay. So, you basically each of those longitudinal modes is oscillating around the center, and they are oscillating at different rates. So, if you do not have all of them oscillating synchronously, you will actually have a continuous emission. Okay. So, that actually gives you another idea. It says that if I am able to synchronize all these longitudinal modes, then I can produce short pulses from the laser. How short? That depends on how wide my spectrum is. If I have a large gain bandwidth and I am able to sustain oscillation across a large gain bandwidth, larger the gain bandwidth, shorter the pulse. Okay. And that is a very important concept. We maybe will come back and look at it in a little more detail later on, but we have something called mode locked lasers. Okay. All the longitudinal modes are locked. When you go through certain procedures to make sure that all the longitudinal modes are locked, then you can actually produce short pulse lasers. How short? People have already done femtosecond pulses. There have been demonstration of attosecond, hundreds of attosecond pulses also. Attosecond is 10 power minus 18, right. So people have demonstrated that also. Okay. So that is an important concept to understand. Although I show all this in spectrum as equally spaced lines and all of that, in reality these lines are not phase locked, because of which you actually have a continuous output as a function of time. Okay. So, come back to this. If I write this in terms of the signal flux, I can rearrange terms and I can say that this is going to be equal to we do not have to say in terms of mu. So, that is in terms of phi s is going to be given by phi sat multiplied by gamma naught of nu divided by alpha r minus 1. Okay. But this is valid only when this small signal gain is greater than alpha r. Without that, what do you have? You essentially have 0 signal photons. If you have less than or equal to the small signal gain coefficient is less than or equal to the resonator loss coefficient. Okay. So, now I can write this slightly differently, since I know that we already seen that at the threshold the threshold inversion multiplied by sigma of mu equals to alpha r, I can just write this as phi s of nu equal to phi sat. Gamma naught can be written as n naught multiplied by sigma, but in the denominator you have n threshold multiplied by sigma. So, the sigma would get cancelled, minus 1 for n naught greater than n threshold and 0 otherwise. Right. So, we are basically saying that there is going to be a sudden change in the signal photon flux around that threshold. Once you reach that threshold condition, you would have a sudden change, and that is what we are showing over here. So, all that action happens around this threshold over here, right. So, below that threshold you do not have, I am saying 0, but technically there are still some spontaneously emitted photons, amplified spontaneously emitted photons and all of that, but there is a sudden change when you go beyond that threshold inversion. Okay. So, we are out of time. Maybe I can just graphically represent this before we break off. So, phi s as a function of n naught is showing something like this. So, phi s is 0 below n threshold, and phi s starts increasing rapidly as you go to higher n naught, which is actually representing the pumping rate, right. So, how do you get higher and higher n naught? By going for higher and higher pump power, right. So, that is the picture that we have as far as the laser is concerned around threshold. So, let's stop at this point, and we will pick up from this tomorrow. We will look into specific characteristics of the laser.